Have you ever seen a curve function and really wanted to find the length of part of it?
Yeah.
Did you try with the ruler?
Yeah.
Did it work?
No.
Then you need to learn the arc length formula.
Now the formula for arc length is L equals to the integral from a to b of the square root of 1 plus dy over dx squared dx. Now how do we get that? Well, let's say you have a curve like this. You might want to approximate it by drawing 2 points, but obviously this is not a very good approximation. But if you keep drawing more points and connecting the dots, then you'll get a closer and closer approximation until you have an infinite amount of points here. The arc length is represented by the summation of the individual distances. If you have an infinite amount of little distances, then that could approximate the arc length pretty much exactly. So that's the limit as n goes to infinity, n summation I equals 1 from the two different points pi and to pi plus 1. Now you might be wondering, how do I get this from this? Well, today's your lucky day if you're wondering that, because I'm about to prove it for you. Okay, so in order to prove that the sum of all these little distances equals to the integral from a to b, square root of 1 plus f prime of x squared dx, use the mean value theorem. If you have all these little points, the mean value theorem states that there exists some number in between this point and this point where the derivative equals to this slope. So it pretty much looks like point slope formula like this. F of xi minus f of xi minus 1 equals to f prime of ci times xi minus 1. You can replace this with delta yi and this one with delta x. Notice how this one has an I subscript and this one does not, because the change in y changes as you go up. So like this delta y is a lot bigger than this delta y, but the delta x's are the same for this proof. All right. Okay, so remember our little distance formula earlier? This is the distance formula between 2 points, and that is delta x squared plus delta y squared square root. And you can replace the delta y I over here in place of this delta OI. And you keep going, factor out the delta x squared to get this, and then you simplify that, and then now you can plug it back in to this, and that is this. And now if you look at this, it looks oddly similar to the form of a definite integral. And since 1 plus f prime of c squared and square root is continuous, then you can write this as a definite integral, and that's the integral from a to b, square root of 1 plus f prime of x squared dx. All right, so here we're just finding the arc length of a line from the x value of -1 to 3. So we just use the integral formula again. Don't forget you can write f prime of x as dy over dx and square. That's the same thing. It's just Leibniz notation. First, you need to find the derivative of y equals 2x minus 5, which is 2. And then you put in your bounds, which are from -1 to 3. For the arc length formula, you really don't need to find the y values, but you'll need to find that for the distance formula. All right, so you just plug and chug. 1 plus 2 squared, it's from this, and then you square it. Equals to root 5, and then you can take the integral of this and you get this with your bounds of -1 and 3, and then plug and chug. 3 root 5 plus root 5 equals to 4 root 5. Now moving on to the distance formula, I found that the distance formula was actually like longer and more tedious. If you have really short-term memory and forgot your distance formula, it's root the square root of delta x squared plus delta y squared. You probably learned this back in middle school, but here's a refresher. All right, so you just plug and chug this. Don't forget you need to find your y values first. So when x is -1, y is -7. When x is 3, y is 1. All right, so you plug in your -1 here, and then your 3 here. So it's delta x -1 minus 3, square that, plus delta y squared, -7 minus 1 squared. You're left with this 16 plus 64 square root. What I did from there was I factored out the 16 and then bam, it's really quick, really easy. Yep. Okay, moving on to the formula for the arc length for polar curves. Right off the bat, you'll notice that the formula is pretty much the same, except instead of 1, you have an r squared. The derivative squared is still the same thing, except you're doing it in respect to theta, and it's dr over d theta instead of dy over dx. Move on to an example.
Find the length of a cardioid, r equals 1 plus sine theta.
So it has bounds from 0 to 2 pi. That's the whole thing. Cardioid starts from here and just winds up there. And you can just plug things in. Don't forget to take the derivative first so you can plug it in here. 1 plus sine theta squared plus cosine squared, because that's the derivative of this. Don't forget to square root everything. After some simplifying, you are left with 2 plus 2 sine theta d theta. The final arc length topic I'll be talking about today is the arc length of parametric and vector functions. If it's a plane curve, you just have y and x's. If it's a space curve, then you'll have an x component, a y component, and a z component. It's pretty much the same thing. You square all the little derivatives of each component, and you take the square root of that. Don't forget the integrals. Both of these can be written like this, because when you take the derivative of an r function, you need to take the derivative of the individual components and add them up. All right, so here's an example.
Find the length of the arc of the circular helix with vector equation r equals to cosine ti plus sine tj plus tk from point 1, 0, 0 to point 1, 0, 2 pi.
All right, so if we take the derivative of this r function, we get negative sine ti plus cosine ti plus k. Pretty straightforward. You just take the derivative in respect to t. You square each term and square root the whole thing. And when you square negative sine t, that's positive sine squared. So you're left with 1 plus 1, which conveniently equals to root 2. And then we take the integral of that with root 2 plugged in, and we're left with 2 root 2 pi when you simplify this integral. That's it for my video. Thanks for watching. Hope all of this helped. And if you get like a test where you have to do all the arc lengths, you know how to do it because I taught you so well. Hopefully. Probably not.